Right.
I found this very nice, this picture on your PALS website. And so I decided to incorporate it into my talk. It shows up again later on.
Okay, I will tell you that I was on the phone with my brother and I told him he is a photographer. He does a lot of Photoshop stuff. Like a lot of people holding hands, alternating man, woman, different colors. Like 30 minutes later, he sent me this.
Uh-huh. Yeah, it's good. It's got the whole spectrum of color, and of course, it still doesn't have gender neutral on it. But yeah, I actually cut off the two men on the end because that way you get the right proportion. It's 51% women on this planet. All right.
It might be men Scotsman, men Scotsman.
That too, yes. It could be anything, yeah.
All right. I think it's about time to start. Welcome, everyone. We are happy to have Peter Jipsen here today from Chapman University presenting about the survey of partially ordered algebras. Please, Peter.
Great. Thank you very much for inviting me to speak in this wonderful seminar. I love algebra and logic. It's my passion. And this particular topic, I've spent the whole summer working on it together with Bianca Newell. And it was a great project because I've been thinking about this for a long time, but I had no idea how I was going to do this. So this evolved, and maybe I can give you an idea of how it went so far. And then later, there'll be a couple of results that are joint work with Jose. So here's the outline. We're going to look at what are partially ordered algebras, because there's a whole theory around it that was developed by Don Pigozzi in 2004. Is the preprint or the manuscript hasn't been published yet, but it certainly deserves to be read. And then there's the notion of partially ordered variety. And I'll talk about the scope of the survey and then about the reality of it. The current version, it's obviously still in a draft stage, but it's also the kind of project that's never going to be finished, but it's certainly hopefully going to be useful to, at least to me. That's my metric, but maybe also to some other people. So then at the end, I'll have some results and some open problems. So let's start out with, well, we're not going to review the unisorted universal algebra because everybody in this seminar knows it very well. But it was developed over the last century, and it has these central concepts: signature algebras, homomorphism, congruences, subalgebras, etc. And the underlying universe of every algebra is a set. And so when you try to move from this setting to the partially ordered algebra setting in a kind of generic way, you just have to replace this category of sets, which is underlying the category of universal algebras of a certain type, by the category of posets. And so what we want is that an algebra has a partial order on it so it's not, technically it's not an algebra anymore. It's a first order structure now with some operations and also a binary relation that has to satisfy the axioms of a partial order. And the notation for the dual poset is just going to be a dual, and it's, of course, the order gets reversed. And then you have additional axioms. For every fundamental operation of A, you want that to be order preserving or order reversing in each argument. And I emphasize the order reversing because partially ordered algebras where everything operation is order preserving, they've been studied much more. They're a subcase of the case that I'm talking about here. And Don Pigozzi is the one who popularized this, allowing the order to be reversed in this general setting, because then it is appropriate for logic. That's the main idea, that we have we have to deal with negation, and so we don't like everything to be order preserving. The information of this order preserving and order reversing stuff is considered to be part of the signature. And so there's a bit of notation. I'm deviating slightly from Pigozzi's original manuscript. He used the plus and minus, and I'm using something that has also been used in the setting to describe whether the operation is order preserving or order reversing. You just have this partial operator or dual, this del. So sigma is a function called the signature, and it goes from the set of fundamental operation symbols to either one or del star, which means it's a string of these two characters, and a binary operation that is order reversing would have a string del 1. Because in that case, it means if you turn the first coordinate upside down and leave the second coordinate the same, then the function that you want is actually going to be order preserving. So that's the specification of the signature. Now, in standard universal algebra, I already mentioned the base category is the category of sets. Here we use the category of posets, but I'm not taking a categorical point of view. Don't worry, I'm not doing category theory here. I'm doing universal algebra with the ordering. And the poset category has order preserving maps as morphisms. So the term operations of our algebra do not live in this category. This is a problem for category theory. The way they try to do universal algebra, this particular problem has not been quite satisfactorily solved yet, but we're working on it. But from a point of view of set theoretic semantics, it's not an issue at all. But the point is that as you're generating term operations on the algebra, they are not only not necessarily order preserving. In fact, they can also not be order reversing. If you take a function like something that was on the previous page, which has this order type that reverses one coordinate and not the other, and then you substitute the same variable into both of those slots, you end up with a unary function that is neither order preserving nor order reversing in some cases. Right? And in other cases, it could be constant. And a constant function is always order preserving and order reversing. So the varieties of algebras where everything's order preserving have been studied at least since 1976, but actually quite a lot longer, because lattices and semi-lattices and other lattice ordered structures turn out to be in this class, right? So instances of this have been studied since the beginning of universal algebra. But this having to cover negation and residuation is what makes this newer setting where we also take care of non-order preserving operations very interesting for algebraic logic. And that, of course, was Don Pigozzi's motivation. Now, studying PO algebras is, in my mind, just because that's the algebraic setting for algebraic logic. It fits extremely well. It, in some sense, fits better than the Bloch and Pigozzi setting. And that's also, it's motivated much better in Don's paper. So obviously, a large part of this talk is just advertising Don's paper. Phi less or equal to psi means that phi has psi as a consequence. So this order is related to the logical notion of consequence. And in particular, algebraic proof theory can be thought of as studying partially ordered algebras where each of the fundamental operations is assumed to be either residuated, which means this in general, or dually residuated, which means the next thing, or Galois connection, which is the third one, or dual Galois connection, the last one. These are really patterns for how to solve inequations. And so the aim of this observation is that proof theory is at least a certain part of proof theory, that the display calculi of proof theory are driven by the fact that residuation allows you to replace an inequality like this, where the y is inside the term function or inside the fundamental operation, and then move it to the outside. But of course, you're not solving an equality, you're solving an inequality. And so the thing that Pigosi did in this paper, which is not terribly long and has lots of details in it, is to show that many of the standard notions of universal algebra just straight away generalize to partially ordered algebras. So let's go over what this is. Subalgebra is what you expect. You just take a subalgebra of the algebraic operations, and then the order has to be induced. So you're not allowed to take an arbitrary suborder. You have to take the induced suborder, but the operations on the subalgebra are just the restrictions. Direct products are exactly the same, except you have to also take the direct product of the pointwise ordering on the direct product to get the ordering of the result. So nothing interesting there, but homomorphisms are kind of interesting. Homomorphisms, of course, are the central notion in universal algebra and the category of certain types of universal algebras. And so here is the idea that the homomorphism just has to be an order-preserving function which is compatible with the fundamental operations. Right? That's exactly what you would expect. So how can this be a problem? Well, it's what you do with the order on the, the order on the image is given and determines what order preserving means, right? So this is not a surprise. It's the homomorphic image that requires a little bit of discussion, but surjectivity is exactly the same definition. Injectivity or embedding, you want it to be one-to-one and order reflecting. So there is already a difference, and this just tells you that the notion of isomorphism in this category of partially ordered algebras, you have to take it to be a surjective embedding, and that's in order to have the property that if two things are isomorphic, then it's, if one algebra is isomorphic to the other one should also be isomorphic to the first one. So you want isomorphisms to have inverses. And so a homomorphic image is just the image of the algebra, but what do you do with the ordering on the homomorphic image? You're allowed to pick any stronger ordering, and that's not properly specified here, but we'll see it in a moment. The notion of congruence changes. In partially ordered algebras, we're hoping to popularize this name. I think Pigosi just called them compatible pre-orders, but let's call them precongruences. And these are the notions with which you construct quotient algebras. And so a pre-order, of course, is a reflexive and transitive binary relation. And a precongruence on a partially ordered algebra, that is an algebra with an ordering and a bunch of fundamental operations, is just going to be some pre-order. So it doesn't have to be symmetric like congruences. But other than that, it also has to contain the ordering of the algebra. So it's not based on equality. It's based on less or equal to. The less or equal to is playing the role of the equality in some sense. And then in addition, the pre-order alpha, which is going to be our precongruence, has to be order compatible in the sense that if the fundamental operation is order preserving in the ith coordinate, then you substitute x and y in, and they have to be alpha related. But if the fundamental operation is order reversing, then you substitute y and x in the opposite order, and that's what you would expect. And the set of all precongruences is now a bigger set than the set of congruences because, well, you get a congruence from a precongruence by just intersecting the relation with its inverse. And this intersection, this congruence, is actually not necessarily a precongruence, because you may lose the property that you're including the order. Now, to see an example, we'll, on the next page, look at some examples. So, but first, talk about quotient algebras. You just take the same notation. We call them A factored by alpha, or this is actually due to Don, and you define the factorization comes from the alpha hat, which is this congruence associated with the precongruence. And then the operations are just induced on these congruence classes as usual. But what is the ordering on the quotient algebra? Well, the ordering is given on the classes exactly by the representatives of the classes being related by alpha. And this gives you a partial order, because we are factoring out by the equivalence that alpha is based on. And it gives you a congruence, or it gives you well-behaved operations because of these two properties here. So that's, of course, exactly the way you want to design this stuff. So it's pretty much you do what needs to be done. And that's what Pigosi, and I should mention that Pigosi did this together with Katarina Palasinski in the 90s. And you know, in 2004, this manuscript was put on the web, I guess. And so now let's look at the varieties. So if you have a class of partially ordered algebras of the same signature, you're going to have what is called the partially ordered homomorphic images. These are slightly different from H. That's the key idea. That's why I'm calling them H sub P. They're for partial, P is for partial order, or P is for Pigosi, because this is one of the key differences. The other two, S and P, behave the same way. And you call K a partial order variety if it is closed under H sub P and S and P itself. And Pigosi then proved the standard result that H sub P SP of K is the partially ordered variety generated by K. And I guess it's a definition at this point, right? No, that these two things are equal is like the result that Tarski proved for universal algebras. And then here we have the model theory. You have inequations, you have the models of these inequations, and the Birkhoff theorem that's relevant here for partially ordered algebras is this result that is in Pigosi's paper. So it's just saying exactly what you think, that partially ordered varieties are determined by inequations, and that can include equations. Right? So let's see some examples. Well, the class of po-sets is actually not so uninteresting, because first of all, the class of sets is a variety of universal algebras, but it doesn't turn out to be a variety of partially ordered algebras. It turns out to be a quasi-variety. That's one little caveat that's on the next slide. But here, let's start with pos. Just take all po-sets, right? It's, you have no fundamental operations. And now, if you take this H sub P, homomorphic images, if you start with any set, then you can get an order-preserving map to any po-set, that, and it can be an onto map to any po-set that is cardinality less than S or equal to S, because you're allowed to add comparabilities on the image side. That doesn't affect the whether your homomorphism is order preserving or not. It'll still be order preserving. So in fact, the variety of po-sets is generated by the two-element po-set under the operations H sub P and S and P. And it has only one proper subvariety, PO subvariety, which is the trivial variety, X less or equal to Y, everything has to collapse. Now, meet semi-lattices are a PO variety with a slightly different axiomatization. You just assume these three very simple axioms for meet. X meet y is less than x meet y is less than y, and x is less than x meet x. That's enough. From that, you can prove associativity of meet. You can prove that, for example, meet is the greatest lower bound. Right? This property can be easily derived from these three. Well, there's something in the background going on here a little bit. Meet is order preserving by this assumption. Meet is order preserving in both arguments. And for lattices, you have to add three more equations. So I just like to say, I mean, this is due to, this was well known to Bloom and other people before that, of course, because this is actually how we do lattice theory and semi-lattice theory and so on. But it's interesting because it brings this to the level of the definition. Now, my favorite is this class of residuated magmas, and left residuated magmas are even simpler, and some people have heard me talk about these things before. It's just the law of residuation, but now you have to write it as an inequation in order for it to qualify as an axiomatic basis for partially ordered varieties. And I see I need to speed up a little bit, but not too much. But okay, so again, these are interesting classes, and at the end of this talk, I'm going to have a slide that motivates that if you add associativity here to, say, to number 5, that's really very much like an extension of group theory. The associative semi-groups together with the residuals and an order are a very smooth extension, I mean, a vast extension of group theory. So in some sense, it's not as easy to handle as groups, of course, but it still has many applications. And of course, it's a reduct of residuated lattices, which is why me and many of my colleagues care about these things. And then partially ordered groups fit into this setting because you have order preserving multiplication, you have a constant where the sigma, the signature of a constant is just the empty sequence. And then you have order reversing inverse. Plus you also have to add the group axioms. The standard group axioms are equations, of course, and equations are inequations. So now, quasi-varieties of partially ordered algebras are very unsurprising. They are just quasi-inequations semantically. I guess syntactically they are determined by quasi-inequations, and the semantics, they are just the models of these quasi-inequations. And then Don also has the result that he has another result that also says this is something to do with direct limits, but one of the results is what I put here on my slide, that it's characterized the same way that it is characterized in universal algebra, because H is not there, right? So now H is not an issue. The class of sets is not a partial order variety. And here's the reason. If you want to make sure that your po set is actually just a set, you have to assert that the partial order is trivial. And the formula that does that is to say that if x is less than y, then x has to be equal to y. And so it tells us that this is a quasi-variety, at least by this definition, because to get sets, you have to take the models of an empty signature of this formula. But why is it a proper quasi-variety, right? Some quasi-varieties are still varieties, so I haven't proved that yet. But at least I can convince you maybe that you can get it like this. You only have to take products of two-element sets to get very large sets. Any set can be seen as a subset of the power set of under equality. And S in this case just takes subsets. So this is really just going to give me all the subsets of big power sets. That gives me all sets, right? Doesn't give me any partially ordered sets. That's the point, I guess, right? So they're all trivially ordered. Now, Birkhoff's rules for equational logic give us an elegant and complete system for deriving all equational consequences from a given set of identities. And this is why we love equational logic, especially the computer scientists who wrote a lot of tools to do this for us and came up with, yeah, that's a good question. I'll get back to that. So this can also be generalized for posets, and this is not new, of course. This is the system for deriving inequalities. So you start out by saying that if you have a set of axioms I, which are inequalities or equalities are allowed in there, but you can just write them as two inequalities. You can define all the derivations of them to be the smallest set containing I, which is closed under these rules. And one of the first three rules say that you're closed under reflexivity, symmetry, anti-symmetry, and transitivity. And then the fourth one is just the standard uniform substitution rule. Because variables are universally quantified, you can substitute any term into uniformly into a variable. But then for equations, you can do the replacement rule anywhere in any term. But for inequalities, you can only do replacement if the order is respected. And that means the term has to either be order preserving if you're going to substitute it in like this, or order reversing if you're going to reverse the S and the R. So that's what you'd have been doing all your life when you've been working with inequations, but that's the system that you have to use officially in this setting. Now, that's the brief survey of how universal algebra extends to partially universal algebra. Probably you didn't learn anything new, but the message is, of course, it's almost the same. And so the scope of the survey that we did over the summer is we took this, old list of mathematical structures, which in my case dates back to 2003, I think I said, some talk I gave in Chicago. And recognizing that almost all the classes of algebras on that list were ordered algebras, I decided let's just make this specific and let's use the right framework for it. And so now it was converted, and this is largely due to the tireless efforts of Bianca Newell, who was helping me with a huge number of details because we wanted to revamp it and redo it in a new way. So in this form now, it's actually more like it's a PDF file at the moment, and it's available, but it's certainly still a draft. And it covers about 500 classes of partially ordered algebras. Most of them are actually partially ordered varieties. And it's organized in this fashion. So there's the class of just partially ordered algebras, but then it quickly turns into the standard join or meet semi-lattice ordered or lattice ordered or distributive lattice ordered algebras. And then there's one section that is not even a quasi-variety. We're looking just at totally ordered because they show up a lot and have their own nice properties. And then there's Boolean ordered algebras, or Boolean algebras with operators is a large subclass of this. And then, of course, there are some unordered algebras because universal algebra is contained in partial universal algebra, partially ordered universal algebra. And so, yes, well, so there are these chapters, and there's an introduction, which that's the main reason why I haven't shared this file yet, but I'm willing to share the draft, except with the caveat that the introduction is completely junk and needs to be redone. So, but maybe there's some interesting tidbits in there that you need to understand the rest. So the purely partially ordered algebras are just in this top chapter, because the other ones the order is actually definable. So it can be avoided to some extent. But here's what the introduction to this first, chapter 2 is the first class's thing looks like. So at the beginning, there's a picture. It outlines the the largest class, or not largest, but the smallest theory, right? These classes are ordered by their theories, and partially ordered sets has the smallest theory here, is at the top, and then it descends from there. And when you see dotted lines, it means that signature is being added, and when you see solid lines, it means that just equations are being added. And here are the examples that we looked at. The left partially ordered magmas, left residuated, or the residuated partially ordered magmas, and the partially ordered groups. But there are many others, and some of the names are already known from the literatures. Others names are using some kind of naming scheme, and that's explained in the next slide, I guess, a little bit. So what does the survey really cover? It covers the signature that consists mainly of a binary operation, dot, lattice operations, and some constants, and then the residuals. But that's already quite a lot. It also covers some unary modal operators, and in fact, I mean, it's not fixed to a certain signature, so things can get added to the survey that require special notation. And the naming convention is, I mean, you have to name things somehow in order to say what you're talking about, and some people like it, some people don't. Sometimes it's trying to be fairly standard, like mon for monoids is probably quite standard by now. So each of these classes, they are defined by some axioms. And so the website that I had over the last 2 decades now also had some properties listed there, and these properties were transferred. But the idea of the survey is that we make the list more reliable. And so currently it's in the form of LaTeX, and there are tools with which we can check that some aspects are correct. And so this is not quite fully implemented yet, but it needs to be used in this setting to make sure, for example, that if a class is congruence distributive, then all of its subclasses will also be congruence distributive. And of course, this is easy to do in your head, but if you're trying to do this in a file with 500 classes and you're inserting a new class, you have to make sure you do it right, or you have some tools to check it in order to keep it somewhat reliable. And in some ways, these tools are interesting to develop, but it takes a while to get it right. In the survey, each class also lists some finite members, and mostly the aim of these finite members, they don't have to be finite, but the aim of the examples that are listed in each class is to show that the class is different from its subclasses, so that it deserves to be in the survey as a new class. And so here, for example, are small po-sets or semi-lattices, lattices, and so this list of, say, distributive lattices starts with a 5-element lattice, because 4-element or lower distributive lattices are either chains or Boolean algebras, so they already got pushed into lower later chapters as examples, at least by name here. And so this is just the ordering. And then on the basis of this ordering, we have to add additional operations. And so, for example, here in a class which is called in-pocrums, or involutive partially ordered commutative residuated integral monoids, right? The abbreviation pocrum, I think, is due to Bloch. Bloch and Pirosi probably, and it's the involutive ones there. Well, there's a fair amount of variety possible, and here's an example of one that has a po-set as base rather than a lattice order or a chain. So the chains have been studied a lot more because they're easier to handle, but these things have not been studied much, and there's actually 3 of them. So in the survey you would be able to find this, but there are not a lot of examples yet because these have to be computed still. but here's the format in which they would appear. And then you can at least tell that there are some that are poset based, and the poset doesn't have to be a chain, for example. And still they can be involutive. The most interesting aspect of the survey, which was sort of started in the previous web pages, is this fine spectra analysis. So the fine spectrum of a class of models is just the number of models up to isomorphism for each of the small cardinals, 1, 2, 3, etc. I mean, the definition actually goes through all the cardinals, but we're only going to be able to compute the small numbers for very tiny models if they exist. And for abelian groups, for example, the fine spectrum is the number of groups of each size. And there are 2 abelian groups of size 4, but there's only 1 abelian group of size 6. Whereas if you look at the MV algebras, the sequence looks a bit similar, but then it turns out there are 2 MV algebras of size 2. And that immediately tells you that MV algebras are not term equivalent to groups, because they would have had to have the same fine spectrum. And for monoids, groups and monoids are not, you know, I mean, even if I had taken commutative monoids here, the fine spectrum behaves completely differently because there are huge numbers of them very quickly. And so the structure of monoids is much wilder than the structure of abelian groups, which is quite well understood to the point where we can really count them, right? If we are willing to believe that we know prime numbers. And here's what we did with these spectra. We created a list. So we had 500 classes and they're organized in some way. But the spectra can be organized just by lexicographic order. So at the end of the survey, there's an appendix, and it just lists all the spectra that were computed. And so there's some interesting questions that come up here, because, okay, some of them are not easy to compute here. We didn't get enough terms to see whether these spectra are somehow numbers that are already known. But here, for example, the number of magmas, these are just unordered binary operations, they can be counted exactly. And that's reflected by the fact that they occur inside the OEIS, that's the Online Encyclopedia of Integer Sequences. But all the other spectra, as far as we can tell, when it says no here, it means they don't seem to be in that list yet. If they're interesting classes of algebras, they probably should be. And some of the totally ordered structures, like totally ordered semigroups, are already there, and they're hard to count. But then, as we were trying to come up with these spectra, we also found some that are already in the list. So these double question marks, I will show you, appear in the OEIS. And let me try this now. If I go out of here, I'll probably cause disaster, but let's do it anyway. Here's my browser, and let's go to my, where am I? Oh, here are my slides, another version of the slides, okay. Where my, if I click on the double question mark, the first one, which is for commutative meet semi-lattice ordered semigroups, then it asks me, do I want to open this link? Yeah, why not? And I go to the OEIS, where it identifies these initial numbers as the expansion of tan of sine x over cos x. This is probably not the right sequence, right? But it would still be interesting to calculate the next number and at least disprove this, right? But if we go to something else, let's try the next double question mark down here. Idempotent totally ordered semigroups. That's down here, and you click on that, and it goes to this number of torsion pairs in the cluster category of type A sub n. And this is sort of interesting. I don't know. Yeah, you can see my pen here, right? I even calculated the next number, and the 2,274 is accurate. And so there, if you read this entry, it obviously has something to do with combinatorics. It's about some Ptolemy diagrams and so on. And it's accurate with 6 digits, I mean, it's up to size 6. And now the question is, can one prove that this is always going to be the case? Oops. All right, make sure I can get back to my talk. Good. So in this list, the fine spectra, of course, go on for like 500 of them, but there are more double question marks. And so quickly, the original structures database versus the current survey, well, the whole project, the original project started in 2003, and it wasn't great, but it still exists. Some of the entries there are incomplete because it's, I don't know, it just, you know, the most important part of a class of structures is that you give them a name and that you've studied something about them, that you're interested in them. The rest of the information is usually easy to derive. And then you have, we put them into this, what we call computable LaTeX document, which just means that the LaTeX is very standardized and you can run Python programs over it and read stuff from it. And also write stuff back into it. And here's the link to Pigozzi's original paper on which this survey is based. And of course, I mentioned this already, Bianca was the person who did all the detailed stuff, you know, and my ideas that she also kept me from having too crazy ideas that would be too much effort. And the survey is not finished. It's going to continue to be updated, I guess. And it has many navigation links in it so that you can browse the file, because you want, you know, we have tools to calculate the things that are in the survey. Many of these things can be calculated also with the universal algebra calculator if you play some tricks. But having them there to be able to browse is the important aspect and get some ideas. And you can get a draft if you come and look at these slides. Now, the results about po-algebras that I briefly want to mention. If the order is equationally definable, then the congruence lattice and the pre-congruence lattices are this isomorphic, and there's actually nice maps between them. And this is the notion of algebraizable from standard algebraic logic, not the ordered version. So when, after the summer, I have started looking at this with Jose Gilfers a bit. And one question we had was, does Johnson's lemma hold? And so Jose actually just managed to prove it and check it, and it works. So the consequences of it also are valid. But one thing that one needs is some examples. If the examples are just the standard examples where the order is equationally definable, then you don't need the extended version of Johnson's lemma. So the only examples that I've come up with so far is they're somewhat trivial. You can take a subrelation of the lattice order, and that will still be a partially ordered algebra. But it will be pre-congruence distributive, and therefore it will behave you know, according to Johnson's lemma in the lattice of partially ordered subvarieties. And another observation is that for any partially ordered algebra, the connected components of the order are always the kernel of a homomorphism to an unordered algebra. This is not too hard to show. And I didn't know it. I had to come up with an argument for that. Sorry, I don't have time to show it, but we'll get to some more interesting stuff in a moment. You can talk about partially ordered clones. It's a clone within ordering on it, and it's generated by operations that are order preserving. Now, I don't know much about clone theory, and there are people in the current audience that know 1,000 times more and will probably tell me that all these things are already well studied, but let's see. A partially ordered clone is a clone that is generated by operations that are order preserving or order reversing in each argument. And in this post lattice now, say, of 2-element clones, there are 3 clones that are not partial order clones. They come from the the order 2 addition, or if and only if, or this ternary operation. And there are 3 where I don't actually know, but they will be trivial to answer. And all the remaining ones are actually partial order clones. So let's look at the remaining ones here. This is the clone lattice of 2-element clones due to post. And so the ones that are known to not be partial order clones are here. The 3 where I'm currently still not 100% sure, they are probably not either of these. But the rest of them are all generated by operations that have the nice property of either being order preserving or order reversing in every coordinate. And this is with respect to the 2-element lattice, or the 2-element set being ordered as a 2-element chain. Now, in 2017, Alexander Kurz came up with an argument, and this may also be well known in clone theory, but just to show that the clone of all operations is in fact a partial order clone, at least if the poset is bounded. Right? I think it's true in general, but I haven't been able to come up with the detailed argument. But here's an argument that works, and I don't want to. It's pretty straightforward, but you have to make sure that you take an arbitrary operation G on a poset, and you want to write it as a composition of operation F, which is order preserving in this case, and another operation D, which is order reversing. And you can do it just by making this definition. So what is this operation D? D stands for dual. It just takes the poset to its dual, but it's the identity relation. So it's actually order reversing. And so you can, by defining F to be on twice as many coordinates, you can get enough space to do this for an arbitrary operation G. Residuation, this is the motivation for me to study these things, to not necessarily have to have the lattice orders and still be able to handle residuated operations in a proper algebraic context with precongruences and homomorphic images and so on. And so here is the residuated partially ordered magmas. They are easily defined as a poset together with a binary operation and its residuals. So the residuations just have to satisfy this if and only if condition, and then it will follow that you have exactly this order type. So it falls into Pagosi's type notion, and you also have these order preservation. Yeah, that's basically what I'm arguing here. And you can rewrite these as inequations. We've seen the inequations earlier, but when you do that, you can then prove that every connected component is up and down directed for an residuated partially ordered magma. And this was a surprise to me. And here's where the argument is with your nice picture. If you want to talk about connected components in a poset, they have zigzags in them, right? So we have here X going up to Z1, down to Z2, up to Z3, these type of zigzags. It's kind of like the arms of these people here are a nice zigzag. And what you have to prove, so if X and Y are in the same component, then there is a zigzag from X to Y. And what I want to show is that then there has to be a upper bound of X and a lower bound of X and Y. So, and the argument is that if you have an upper bound of two things, then you actually also have a lower bound. And this term, so we have to check that in a in a partially ordered residuated magma, this term is always below both A and B. And that's not hard to do because the proof theory helps us here, right? If you fiddle around with this, I think you will find the proof. And the reason you can do it, even though it's an ugly term, has to do with the smoothness of the proof theory. You can make wrong decisions, but not too many. Right? I mean, it's like you can make one wrong decision and then after that you make the right decision and you prove this. And then you do the same thing with the bigger term, which does it the other way around. And residuation is not self-dual, so you need both of these observations. And then after you have that, you see that inside a zig, like this lambda, you have 3 elements, and now from these 2 lemmas, you get a lower one. And then it means you can now take with the next zag, you just repeat this and you'll see that this gives you a lower bound of any 2 elements in a component and also an upper bound. And that means that in the finite case, for example, these components have to have top and bottom. So this is a restriction that comes just from having residuals. Maybe there's an easier argument, but I would love to hear it. The last result I want to mention here is about residuated partially ordered semigroups. They are also called Lumbeck algebras. And this is to show that they are really generalized groups, right? If we add the quasi-inequation that makes the order an anti-chain, then we get exactly the partial order quasi-variety of groups. And this is not a variety. Why? Because if you take the group of integers with equality and you take its homomorphic image, which is all the homomorphic images, those homomorphic images actually include the linearly ordered integers, because there's a homomorphism from here to there. It's the identity map, right? And so this H sub P enlarges the class into something that includes, that violates this quasi-identity. And Pigosi, at the end of his paper, of his very nice paper, shows that for left residuated unital PO magmas, you don't even need associativity. You have what is called a partial order Maltsev term. And it's just this term here. Maltsev term here means it satisfies these inequalities, and the term has to have this order type. So in the middle variable, it has to reverse the order. In the other 2, it has to preserve the order. And with this term, you can show that precongruences are permutable. Now, the precongruence lattice of an algebra is vastly bigger than the congruence lattice in the general setting. But still, it becomes permutable. And currently, this is the only Maltsev condition that's known in this area, because the other proofs, I mean, even the proof of modularity doesn't work. So here is a list of questioned and open problems. Is there a characterization of the partial order clones other than finding a generating set? So I want to be able to know if a clone is generated by order preserving or order reversing in each argument operations relative to some given poset. But I have a hard time making that decision. So if there's some clone theory that helps me, I would love to know about it. Can we tell whether the clone is generated by residuated or is operations which have this property in each argument? So there has to be a free function, but is also algebraic in the categorical sense, but some category theory still needs to be worked out. And then finally, we need more examples of precongruence distributive algebras, natural examples. I mentioned the Maltsev condition already. Can it be strengthened to give modularity or distributivity? That would be interesting. here, this is the question with the double. When I briefly looked inside the OEIS and found an interesting sequence, it's the challenge here is to describe the structure of finite totally ordered bands. Now, they've been described. I would guess they have been described because the structure is not that complicated. The structure of semigroups has huge amounts of work, but counting. This is about, have they been counted properly? And if so, then at least we should find the result and put the reference into the OEIS. So this table of fine spectra has other such challenges in it. So if you want to, you can take a look at this current draft survey. Notice it's a draft. I've said draft many times. Please forgive any mistakes. And there have to be many more references put in it. But it's an interesting document for me at this point, and so I thought I'd give a talk about it. Thank you very much.
Thank you.